start with on-off control of current. Now a system like this can be used in an alarm system. We got figure 11.15. 11.15 shows a SCR and basically with a switch S1. Now when we close switch S1, what happens? We put a positive voltage on the gate of the SCR. When we put a positive voltage on the gate of the SCR, we will basically trigger the SCR and there will be a current flow from my anode to my cathode. And that SCR will stay in conduction as long as my current is larger than my holding current. That means the only condition under which we will turn off the SCR, we can even open switch S1, we open that switch, it will stay on until my current drops to a value lower than the holding current. Now the only way to turn it off again is by closing switch S2. When we close switch S2, the current will flow through that and the current will drop to a value lower than the holding current, and that is the only condition under which this SCR will turn off. Alright, the next circuit, that is on page 563. Alright, there's an example. Let's quickly look at the example. There's example 11.3. You can go and work through the example 11.3 on your own for homework. You can go and do that example. The next circuit, that is on page 563, half wave power control. Now where do we use circuits like that? Sometimes you got light dimmer circuits. They don't use SCRs, but they use triacs to dim the intensity of a light. We can use it there. Speed controls in these small drilling machines, there they won't also use a SCR, they will rather use a triac to do the job. But now we're going to look at this half wave power control. Why did we talk about half wave? Because you will notice we got only one SCR in the circuit. Now we know a SCR or a diode got the capability that current is flowing only in one direction. That means if I think about my input wave, that means only half of the power will be available. During my positive cycle, when it's positive here, negative there, the diode, the SCR can conduct. For the negative cycle, when it turns around, when it becomes negative positive, that SCR will be reverse biased and we won't be able to get any flow. Now let's go and have a look at the operation of this circuit. We go to page 564. Alright, this is figure 564. Let's have a look at figure A, when we're going to look at 180 degrees conduction. That means I will have conduction for 180 degrees. Now that means we're going to trigger here at basically 0 degrees. You can see here we got a voltage divider. R1 and R2 forms a voltage divider with a variable resistance there connected to the gate of the SCR. That means you can see we're at the top position there. That means that thing is going to trigger at around about 0 degrees. That is going to work exactly the same as a normal diode. Because a diode, if you go higher than 0.7 volts, it will go into conduction. That means now what will happen, that will be my positive cycle. That means it will be actually positive, negative, and then I will get a flow like that through the SCR and through the load. That means across the load, I will have basically that. You can see that is exactly like a half wave rectifier. That means I got now maximum power in this circuit, because the negative cycle, that means this is the negative cycle. What will happen, then it will become negative there and positive there. The SCR will be reverse biased. When it's reverse biased, we won't be able to get any conduction. That is the A one. We go and look at B. When we're going to basically fire at 90 degrees, when I trigger at 90 degrees, that means I will have basically only that half of that 180 degrees conduction. That means I will have half that amount of power. That means I will have conduction from that point to that point. Let's go and have a look. That means now I adjust my variable resistance to, let's say, around about that position. And now when I reach high enough positive on the gate of the SCR, when that thing increased, the SCR will trigger and we will have conduction like that through the SCR. That means we will only have conduction for that 90 degrees. That means the conduction will be 90 degrees. For the negative cycle, it's going to turn around. The current will drop to a value lower than the holding current, and that will basically eliminate my flow. When it drops to a value lower than the holding current, then it will turn off. Everybody with me? That means the only condition under which the SCR will turn off is when my current drops to a value lower than my holding current. Let's go and have a look at C. At C, I got a conduction for, I'm going to trigger at 45 degrees. That means 45 degrees, there's 0, there's 180 degrees, there we got 360 degrees. I'm going to trigger at 45 degrees. That means you can see the slider of the potentiometer is higher up. I'm going to trigger at 45 degrees. That means I will have conduction for 135 degrees. That will be the conduction period. All right. At that point, it will go through 0. Current will drop to value lower than holding current, and the SCR will turn off. All right. That is basically that we talk about phase control. That means I can control the amount of power to my load. One important thing here, with a circuit like this, we can only control basically from 0 to 90. That means the control can only take place from there to there. All right, let me make another drawing. We look at this, we can only control from 0 degrees to 90 degrees. Why? I will show you why. Because, let's say for example, I want to fire at 45 degrees. There's 45 degrees. Or, let's go and draw a line across here. That point will be 135 degrees. But that voltage and that voltage is exactly the same. That means this circuit works on the voltage given to the SCR. Now in this case, this thing increased. It increased from 0 to that value. That's why if I want to select that point, it's going to be exactly the same voltage. That's why it will always switch when it increases. That means we can only basically control from 0 to 90 degrees. You won't be able to control after 90 degrees with this type of circuit. You will get other circuits that will be capable of doing it, but with this very simple circuit, we can only control from there to there. All right, let's go and have a look at this example. Example 11.4 on page 564. They state, show the voltage waveform across the SCR in figure 11.19 from the anode to the cathode ground in relation to the load current for 180 degrees, 45 degrees and 90 degrees conduction. Assume an ideal SCR. What I mean by assuming an ideal SCR, we assume there's no volt drop across the SCR. When it's conducting, it will act like a short circuit. When it's off, it's going to be completely open. All right. Here they give us a circuit. The supply voltage or the source voltage is 120 volts. R1 is a 10 kilo ohm, R2 is a 500 ohm variable resistor, and the load resistance is also 100 ohm. Alright, now they want, first of all, they want the load current, they want IL. There is IL, my load current, and they want the voltage across the SCR. They want VAK, the anode cathode voltage directly across the SCR. Alright. That is the two things we must now go and draw. Alright, first of all, they talk about a conduction of 180 degrees. Alright, if I will have conduction of 180 degrees, I will basically trigger at 0 degrees. Here will be basically 0 degrees. I will trigger at 0 degrees, then I will have conduction for 180 degrees. Now, when I got conduction, there will be the load current. The load current and the voltage will be in phase because I got a pure resistive load. They're going to be in phase, alright? That's going to be IL. Let's go just back to the circuit. Now we look at the circuit. When I trigger at basically 0 degrees, I will have IL that will flow through my load resistance and it will give me a volt drop across that, alright? Now, when this SCR triggered, what will the SCR look like or act like? It will act like basically a short circuit. That means the volt drop across this SCR when it's conducting is like a closed switch. The volt drop is going to be 0, is equal to 0 volts. That's why the volt drop across the SCR for that duration of time is 0 volts because it's like a closed switch. After 180 degrees, what's going to happen? The current will drop to a value lower than the holding current. When it drops to a value lower than the holding current, it will basically now the current will be basically, there won't be any current flow because it's like an open circuit, and because it's an open circuit, I will measure the full supply, my full negative supply will be across the SCR because now it's like an open switch. Like a switch looking like that, an open switch. Here it was like a closed switch. Alright, that was for 180 degrees. Alright, for 180 degrees conduction. Alright, let's have a look at the next one. The next one, they say 45 degrees conduction. Please note a mistake in the book because if I look at this 45, I'm triggering at 45. Here we're triggering at 0. Where do we trigger here? We trigger at 45. The conduction is going to be 135 degrees. That means I think the best way to rectify the problem in your books, write down, if you look at the question, relation to the load current for 180 degrees, then it shouldn't be 45 degrees. It should be 135 degrees. That means here we got conduction for 135 degrees. That means the question in the book is wrong. Change it, rectify it to 135 degrees, please. It's not 45 degrees, it's 135 degrees conduction, alright? Now, that means we trigger here. We trigger at 45 degrees. That means that trigger pulse should be 45 degrees. Now my SCR is conducting, I got current. That means before that point, the SCR also looked like an open switch. That's why we get that part of the wave. When it's conducting, it looks like a closed switch. And the volt drop across the SCR is 0. Negative cycle, SCR is completely off. The complete negative supply voltage will be across the SCR. Alright, I repeat, please make sure we trigger at 45 degrees. The conduction is going to be for 135 degrees. Alright, let's go to the last one. The last one they say, and degrees conduction. Now we got 90 degrees conduction. In this case of 90 degrees, at what are we going to trigger? In this case, we're also going to trigger at 90 degrees. That means the trigger pulse at the gate should be at 90 degrees. That means before 90, the SCR will act like an open switch, and the full supply will be across the SCR. The current will be basically zero because there's no current flow. Then when we trigger, we will get basically that current flow, and the SCR will act like a closed switch. That switch is closed now. There's no volt drop across the SCR. Negative cycle, exactly the same. The SCR will be off. The current drop to a value lower than the holding current, and we will get the whole negative cycle across the SCR. Everybody with me? That is basically half-wave power control of a SCR. That is one of the applications. I repeat, please take note, with a circuit like this, you can only have control from 0 degrees to 90 degrees. Only control for that with this circuit. With this circuit of figure 11.7, or let's say the example figure 11.19. You can only have control from 0 degrees to 90 degrees. Alright, on page 565. Figure 11.21. That is also now a practical application where we make use of a SCR. It's quite an interesting circuit. Some of previously work done by you in S1. In S1 you did a full wave rectifier making use of a center tap transformer. Here we got exactly the same. If you look at this part of the circuit, we got a transformer, we got our AC supply, we got a center tap transformer, we got two diodes D1 and D2, and that will give me basically the following output. That should give me an output that's going to look like this. We will have a DC voltage. That will be 0. That will be my V peak. Alright. I will have a DC voltage from my AC supply. Now what will happen? Let's have a look. Due to that, the power is on in this case. That means the AC power is on. We talk about automatic backup lighting circuit. That means I got my supply on, the AC supply is on. What will happen? That means this light will be fed from my AC supply. At the same time, I will charge this battery through R1, D3. I will charge that battery. And now another story. We are going to have a look at this SCR. What will happen? On this side, we will have plus 6 volts. Here we will have a voltage less than 6 volts. That means that SCR will basically be reverse biased. It won't be able to switch on. Alright. That condition will go on. Now let's assume I got a power trip. The power goes off. What is going to happen in this system? The moment the power goes off, we will know that the voltage at this point will drop to a lower value. Now this voltage will be much lower than the 6 volt of the battery. Now I will have a positive voltage on the anode. I will have negative on the cathode. And due to this voltage divider, due to R3 and R2, I will put a positive voltage on the gate of that SCR. When I put positive voltage on the gate of the SCR will trigger, and then it will take energy from the battery through the SCR, through the lamp, and now my lamp will be on. And the lamp will stay on. Let's assume my voltage come on again. What's going to happen? When the voltage or the supply is back in the system, what will happen? The voltage here at that point it will increase. Now it will increase to a higher value. When the moment that voltage increase there, what will happen? This point will become more positive than the battery voltage. When that happens, the SCR will turn off because the current will drop to a value lower than the holding current. The SCR will turn off and the light is going to be fed by means of my full wave rectifier, making use of a center tap. And then when the power goes off again, the whole process will basically repeat itself. That is basically how this automatic backup lighting circuit is working. You will use this in places where there should always be light. Let's say like in a hospital where they have to do operations, you can basically install something like that. The moment the supply trips, there will still be light. Alright, let's go and have a look at the next circuit. That is on page 566. There they give us a basic SCR over voltage protection circuit. Now, the only thing that happens here, we monitor the output of a DC supply. We look here we got a DC power supply. We don't want this output to go to a too high value, but let's say it goes to a too high value. Here we got a Zener diode, and when that voltage goes too high, the Zener diode will become reverse biased and the current will flow like that. Applying a positive voltage here on the gate of this SCR D2. When it apply a positive voltage there, what will happen? I will actually create a short circuit through the SCR to ground and will basically blow the fuse and protect the rest of my circuit. I repeat, when the output voltage of the DC supply goes too high, this Zener diode will go into conduction in the reverse direction, putting a positive voltage on the gate of D2, basically triggering D2, and basically will blow the fuse and basically protect the rest of the circuit. That is a very simple over voltage protection circuit. The final circuit of this part of the chapter is a sawtooth generator. We're quickly going to have a look at this sawtooth generator, how this thing is basically operating. Alright, we got a DC supply, we got a capacitor, we got a SCR, and variable resistors. Now what will happen if I switch on the power? We will notice that this capacitor will be basically completely discharged. Let's assume the capacitor is completely discharged. And now when I switch on the power, I will start charging the capacitor due to the battery through R1. I will charge it like that, positive, negative. Now what will happen? The voltage will increase. The true curve should actually look like this. The voltage will increase. That's the charging curve of a capacitor. When this voltage reaches a certain level, determined by R2 and R3, when it becomes high enough, positive, it will go positive. What will happen? I will basically trigger the SCR. When I trigger the SCR, it will go in conduction and will basically discharge this capacitor like this, through the SCR like that. It will discharge the capacitor and the voltage will decrease. Then, when the current is smaller than the holding current, what will happen? When the current drops to a value lower than the holding current, the SCR will turn off and the whole process will repeat itself. Then it will charge again the capacitor positive, negative. Start charging at positive, negative, till we reach the point where we trigger the SCR. The SCR will discharge the capacitor till the current drops to a value lower than the holding current. Then it will turn off again. And that's why they tell us it's a sawtooth generator. That means it will give me a sawtooth oscillation out. And the frequency will be determined by the resistor and the size of the capacitor and my supply voltage there. Alright, that is basically all that we're going to do today. 11.3. I will come to the different classes and we will talk about the problems. If there's any questions, you're welcome to ask, and we'll go through the questions quickly if there's any questions.